En quart lloc, tenim la presentació de la Libre Space Foundation, una de les comunitats més actives en projectes open source espaials. Creadors, entre altres, de la xarxa d'estacions terrenals satelitals SATNOGS. Per parlar d'aquest projecte tindrem a Fredy Damkalis, un dels seus core developers.
Hello, I'm Alfredo Damkalis. I'm core contributor of Libre Space Foundation and one of the main developers of SATNOGS project. Some words about Libre Space Foundation. It is a non-profit foundation founded back in 2015 with headquarters in Athens, Greece and operations in 4 countries. We are 100% dedicated to space technologies and 100% dedicated to open source space technologies, and we are led forward by the principles of the Libre Space Manifesto. Some of our projects is UPSat, an open source 2-unit CubeSat built from scratch, Cubic, 1P pocket cubes that perform experiments during LEOP, Picobus, an 8P pocket cubes deployer with a low-cost design, and SATNOGS that we are going to present today. So, how it started? Some years ago we participated in NASA Space Apps Challenge, and this is the challenge we faced. A group of CubeSats is deployed from launch vehicles and our space stations. Find a way to receive data from them, store these data and present them, and also try to connect NORAD ID objects and their TLE sets with these satellites, which is also known as satellite identification. Our solution was SATNOGS, an open source global network of satellite ground stations focused on automating the satellite tracking and communication. So, in more detail, we tried to create a cost-effective solution for ground station and automate also the reception and the decoding of satellite data. So we created SATNOGS Client, the software that runs in our ground stations, and also SATNOGS Rotator, a 3D printed rotator that help us to track the satellites when passed over our stations. To orchestrate all these ground stations, we created SATNOGS Network, which allow us to scheduling a batch of observation on all these stations. For scheduling now, we need some information like the transmitter frequency, modulation, and other details like that. So we created SATNOGS-DB to store all these informations about satellites and also to gather all the data from the satellite observations. So where SATNOGS is today? SATNOGS today is an open source stack of several software and hardware projects, as well as services and open data. All these created by contributors like universities, organizations, space agencies, satellites, teams and missions, the radio amateur community, scientists, engineers, researchers, space enthusiasts, and other individuals. So what SATNOGS does? It gathers telemetry and also has telecommand and control capabilities in different frequency bands, and also visualize all these gathered telemetry and data. We also have a big collection of observation artifacts like data from satellites, waterfalls, audio files, and IQ data. We also help for satellites to determine their orbit and also generate TLE sets for them. And we also help and identify satellites. Finally, we record frequency violations. So, during the last years, we have faced satellite missions with several issues. On the ground segment side, missions without ground segment at all, or ground segment not ready or broken, on the start of the mission or during the mission, and in some cases the satellite orbit didn't allow the ground segment to have more than a few good passes per day. Also on the space side, on the space segment side, we know space is hard, so we have satellites with faint signal transmissions, with random transmissions only under sunlight, or transmissions only the first hours or days after deployment, satellites that never transmitted or their transmissions unexpectedly stopped, and satellites with not accurate TLE or orbit prediction. All these issues were faced, and we tried to help all these missions with our SATNOGS network, a network of 254 online stations and almost 150 testing stations that eventually we are moved to online status. So how SATNOGS works? We schedule observations in SATNOGS network. All these scheduled observations are then moved to ground stations. So ground stations know the next passes of satellites. So when satellite passes, the ground station receives its data and also creates observation artifact like waterfall and audio files. All these data are sent back to SATNOGS network, and from there the demodulated frames are forwarded to SATNOGS DB, and also we gather in SATNOGS DB frames from third-party observers. And in SATNOGS DB we have the SATNOGS decoders that get all these demodulated data and decode them to create human-readable data, which later, using SATNOGS dashboards, we can visualize and help the satellite missions. Another aspect is to use the SATNOGS network and STRF tools to identify the satellites, and also to determine their orbit and generate TLE sets for them. So let's do a quick demo and see this workflow. Here we see the SATNOGS DB website. We have some new satellites added. We can see in the first column. We have the latest data that were forwarded by observers for satellites, and the recent contributors that have forwarded frames for the last 24 hours. So let's search for satellites. We are going to search for Bobcat 1. So here we have the entry of Bobcat 1. We see some information, an image, a description and other details. We have also a tab with the map to find out where the satellite currently is. And also we have a tab for its transmitters. Here some of them are inactive with the red color and some of them are active. So we have details for observing the satellite. So let's go back, let's go to the network website, where we can schedule observation for the satellite. So we go to observations. Here we see all already scheduled observations for other satellites over different stations. So we hit the new observation button. We select the Bobcat 1 satellite and we select the transmitter we want to observe. And also we can select the stations that we like to use. We set also a time span. Here is for 1 day, and we hit calculate. So now we are going to get back all the passes over the selected ground stations. As we can see, there are many satellite passes over the stations. So we are going to select one of them and schedule it. Of course, we can select more than one and schedule all of them at once. So here is the observation page and how with all the details about the observation. Some of them, like the TLE, the frequency, the modulation, are requested from the ground station, so in order to observe the satellite. So let's go to already done observations, already finished. Here are all the good ones. Good ones means that we have already verified that there was signal from Bobcat 1 on these observations. So here we see the waterfall artifact, where we can see the horizontal lines, which are the signals from the Bobcat 1. We have also the audio. We're waiting a little to load. We are going to see the waveform and the spectrogram of this audio. Here you can see the lines, the vertical lines, which are the signals from Bobcat 1, and also we have the demodulated data, and some of them can be decoded with ASCII. You see here the signal, the call sign of Bobcat 1. So other artifacts that we gather. Oh, let's see another example of audio. Here is an ISS observation during an Iris contact event. Iris contact events are events where ISS astronauts answer to questions from students or from schools around the world. So let's go to the audio and hear one of these answers. Okay. So another interesting case of observation artifacts are the one of weather satellites, where you decode the data as an image. Here you can see the waterfall where the satellite has sent its data and how it's decoded. Let me open it. Yeah, here. Here we can see the West Europe, Spain and France and other countries. So let's go back to the demodulated data. We said before that we forward all this data to SATNOGS-DB. So let's go back to SATNOGS-DB and see the data tab. Here we see the more recent observers that have forwarded data for the satellite, and also how many of these satellites have been decoded. The decoding happens with decoder scripts, which are generated by kite structs, which are structs that describe how to decode this data. Let's see an example of Bobcat kite struct. So here are different, and here we see the Bobcat 1. So there is a description of the fields, some documentation about the fields, and here is the type and the ID of its field. So we get the demodulated data. We describe for each bit what it shows, and we decode the data and bring them to a human readable form. And having the decoded data in a human readable form allow us to create dashboards for them. So let's see the dashboard for Bobcat. Let me change the refresh rate. So here we see different values visualized, like with the battery voltage or solar panel power, like solar panel input current, temperatures, etc. So these help the missions to have an overview of the status of their satellite. And with this, I'm going to complete this short demo and go back to the presentation. As we said before, another aspect is the satellite identification. So here are two images from STRF tools in the left and IGNOS at the right. You can see on both of them a curved line that shows the expected orbit of the satellite and the signal of the satellite that fits this expected orbit. So here we have a fit, and we can identify that the satellite follows this NORAD ID object. Another aspect is also the TLE generation with STRF tools. As you can see here, we have red dots. These red dots shows the received data from several observations, and we try to fit an orbit to this data. This happens by changing the several variables that exist on the orbit that exist to describe the orbit. So when we fit when we feed these variables and the orbit fits the current data we have, we can generate a TLE set like the one we can see here. So here are some SATNOGS statistics. In SATNOGS network we have more than 400 stations that perform around 5,000 observations per day, and also demodulate almost 25,000 frames per day. And all these with more than 4.7 million observations until now. In SATNOGS B we track almost 650 satellites with more than 1,200 transmitters, and we have gathered from the network and the third-party observers more than 110 million demodulated frames. On other stats, we have more than 50 decoders and dashboards, and we have generated TLE sets, more than 100 TLE sets, and we have managed to identify more than 100 satellites. So, how someone can be part of this project? Here are some of the ways. A simple one that will get you familiarized with the reception of a satellite is to build a ground station. You can start with a simple ground station with just a Raspberry Pi, an SDR device, and an omnidirectional antenna, and then you can build on it with adding rotators and directional antennas or low noise amplifiers, or even capability for transmission. Another way to contribute to the SATNOGS project is by developing software and hardware. As I said, our projects are all open, so you can see the code or the designs, and you can add new features to them, or you can fix some bugs that exist, or even help us to write tests and write documentation about them. One more way to contribute is to participate in ground segment operations, like adding information about satellites in SATNOGS B, like frequencies, transmitters, new satellites that are going to be deployed, etc. You can also create decoders by creating the kite abstracts we've seen, build dashboards for satellites, and also you can help us to schedule observations for special events like the Arch contact we've seen earlier, or new deployments of satellites, etc. So if you are interested to participate, please join us. Here are our websites, the wiki where we gather all the documentation about the operations and how to build stations in SATNOGS and how to get involved in SATNOGS. We have also our discussion forum where the community discuss about new deployments or issues with the ground stations or scheduling new observations, etc. And of course our repositories where all the code can be, or the open source code and designs can be found. Thank you.